In this video, we're going to work on combined energy calculations when we are undergoing a cooling process. The question states that 85 grams of hot water, which are at 90 degrees Celsius, were placed in an ice cube tray in a freezer which is set to a temperature of negative 18 degrees Celsius. And it's asking us how much heat in kilojoules must be removed from the water to form ice cubes. So the very first thing I'm going to do is label the cooling curve that is depicted below. So take a moment, pause this video, try to complete that on your own, and then we'll check in and do it together. Okay. So notice that at 100 degrees Celsius, that represents the boiling point of water, which means that here we can either convert water into steam or take it from steam into liquid. So we're starting off in the gaseous state if we're above 100. And at 100 degrees Celsius, we're going to have condensation, because in this case, we're removing heat, so we're going to condense it down into water. So condensation is really just the opposite direction of vaporization, which means that here we have a phase change. We're going from gas into liquid. And the equation that is associated with that is the heat of vaporization, since that is just the opposite direction. And the heat of vaporization value that is listed on the reference sheet is the following, where it says the heat of vaporization is 2260 joules per gram. So in that region, we are using the Q equals mass times the heat of vaporization equation. Once we get below 100 degrees Celsius, we are in the liquid state. So everything here will be a liquid. And all we're really doing, if we're going below 100 but not quite yet at 0, is we're just cooling that liquid. And there's no phase change here. We're just going from a very hot liquid to a very cold liquid, which means here the equation will be mass times specific heat times the change in temperature. When we get to 0 degrees Celsius, that is the melting or freezing point of water. So if we keep removing heat, we're going to freeze that liquid into a solid. And because there is a phase change here, so this is freezing, and because there is a phase change, we're going from a liquid into a solid. Notice that there is no change in temperature, right? This whole process is going to occur at 0 until everything is completely frozen. So the equation associated with that is Q equals mass times the heat of fusion. There's no change in temperature here. And that equation is listed on the reference sheet right here, and the value for the heat of fusion is listed right there. Okay. Once everything is completely frozen, if we keep removing heat and we drop even below 0, then we're in this range, and this is where everything is a solid, so all the water has been turned into ice. If we keep cooling it past that point, there's no phase change, we're just changing the temperature. So the equation associated with that is mass times specific heat times the change in temperature. So that is the process. We need to know where we are in the cooling curve and which equation is associated with each region. So the next thing I'm going to do is just doodle myself little pictures identifying where I am on the cooling curve and which steps I need to undergo. So take a moment to pause this video, try it on your own, and then we'll take a look at it. Okay, so let's do this. This is saying that we have hot water at 90 degrees Celsius. So 90 would be here-ish somewhere, which means that the very first thing that we're going to do, we're eventually going to form ice cubes, right? So we are here, but we need to get all the way down here, which means the first thing we have to do is cool that water to 0. So step 1, we have cooling. So here we have very hot water. It is at 90 degrees Celsius. We're going to cool that to 0. Now, when we cool it to 0, we haven't frozen it yet. This has not undergone a phase change, but it ended up at 0 degrees Celsius. So for cooling, the equation associated with that is Q equals mc delta T. Okay. Now that we have cooled it, the next thing we're going to do is freeze that water into ice. So now we do have to undergo a phase change, and there's no change in temperature when we are doing a phase change. So the equation for that will be mass times the heat of fusion. So step 2, freezing. And here we have mass times the heat of fusion. Now, once we've done that, that water has now been converted into ice, so we are in the solid state. So here we have ice, and because there was no change in temperature, we're still at 0 degrees Celsius. And finally, it is saying that the freezer is set to -18. So we actually are going to cool that ice further. We're not ending at 0. So the next thing we have to do is cool that to -18, which we'll say is somewhere around there. And because that doesn't involve a phase change, but does have a change in temperature, we're using the Q equals mc delta T equation. So step 3 will be cooling again. And here, there was no phase change. All we did was take that ice and churn it into even colder ice. So still ice, but here the temperature is -18 degrees Celsius. Okay, we have all the steps now. Now we're going to take each of these individually and calculate the actual values. Now with the cooling curve, this is where things get a little bit different because here we're actually removing heat, which means that the heat that we are calculating will be negative. So there are a couple of different ways that we can handle that. We can either use negative values for everything and just express it negatively, or we could calculate everything as positive values just like we do in the heating curves, but then at the very end we can say that energy is being released, which implies that that is negative. So I'm going to do both. And I'll say we'll call this method A. So in method A, I'm going to say keep everything positive. So I'm going to ignore the fact that my ending temperature is lower than my starting temperature. I'm just going to keep this a positive value just to simplify things. And then I'm going to say at the end that energy is being released. And then we'll do method B after that so you can see both. Okay, so we are cooling. That's the first thing we're going to do. The equation for that was, and the mass was given to us in the problem. That was 85 grams. So I'm going to plug that in. And then I need the specific heat value. And notice here, we started with water, we ended with water. All we did was cool that down, which means here we want the specific heat of water, not the specific heat of ice. So I'm going to plug that in. And then we want a change in temperature. So we started at 90, we're ending up at 0. And technically this should be a negative value because we're subtracting 90 from 0. But as I said, in this method, I'm going to keep everything positive. So I'll just say delta T is 90. And we'll just act like that's a positive value. And I'll plug that in. And now we have grams up top and on the bottom. We have Celsius in the numerator and denominator. So those are canceling out and our units are in joules, which is what we want when we're calculating energy. So I'm getting 32,008 joules being released during that step. Now we are freezing. freezing. And the equation for that was mass times the heat of fusion. Mass is the same, 85 grams. And I'm going to look up the heat of fusion, which is listed right here. So I'll write that value down. Okay, and now we have grams in the numerator and denominator, so they cancel out and our units are in joules. So that is 28,390 joules released. And I'm writing released on everything to indicate that this really should be a negative value because it's being cooled. But if I keep it positive, I can say that energy is being released from the system. Okay, and step 3 was cooling. And the equation for that and again, we have to be careful because here we have ice and we're ending up in ice. So we actually need a different specific heat value. We need the specific heat of ice, which is this one. So make sure you don't mix it up with the specific heat of water. We have to know which phase we're currently in. Okay, so that was 85 grams. Specific heat of ice was 2.03 joules per gram per degree Celsius. And then the change in temperature, we're starting at 0, we're ending up at negative 18. So we can say that change in temperature is 18 degrees Celsius. And now the grams cancel out, the degrees Celsius cancel out, and we are left in joules. Okay, that is getting me 3,106 joules released. And I'm just going to add all of these values together. So Q total will be each step added together. And I'm getting 34,602 joules released. And at the end, let me just double check. It asks for kilojoules, so I'm going to convert that to kilojoules. So all we really need to do is 1,000, but I will plug it in. So in 1 kilojoule, we have 1,000 joules, and we're putting joules in the denominator so that they can cancel out because we have joules up top as well. So joules in the numerator and denominator, they cancel out, and that gives us 34.6 kilojoules are released. And because I kept everything positive, I am keeping the term released here because that is indicating that energy is leaving our sample. And it's implying that it should be a negative value. So that was method A, keeping everything positive. In method B, I am going to make everything negative. And again, it's negative because we are cooling. So energy has to leave the system in order for those particles to slow down enough to eventually freeze. So we'll go step by step again. The first thing we're doing is cooling. And the equation associated with that is Q equals mc delta T. And here is why everything will be negative. So to calculate the change in temperature, we are subtracting the initial temperature from the final temperature. And notice that here you are starting at 90 degrees Celsius and you're ending up at 0, which means our final temperature is 0 degrees Celsius and our initial temperature is 90 degrees Celsius. That gives us a change in temperature of negative 90. And that's why everything ends up being negative here. So I'm going to plug that in. Everything else is the same. The grams were 85. The specific heat, here we were in the liquid state the whole time. So we used the specific heat of water, which was 4.184 joules. So everything else, same thing. And now our grams cancel out, the degrees Celsius cancel out. And if you plug that in, you're going to get the same value we had here, but it will be negative. So that will be negative 32,008 joules. And here we don't have to say released because the negative is telling us that that energy is being released. In Q2, we were freezing the sample. And the equation for that is the heat of diffusion. So here I'm going to turn that negative, because here we are cooling it down, we're freezing it and turning it into ice. So that will be negative 85 grams times the heat of fusion, which was 334 joules per gram. And the grams cancel out and we are in joules. So we'll get the same value we had here, but it will be negative. So that'll be negative 28,390. And then once everything is frozen, we are cooling it further. And the equation for that was mass times specific heat times the change in temperature. And again, the change in temperature is going to be the final temperature minus the initial temperature. While here, our final temperature is negative 18 and our starting temperature is 0, which really means that we are subtracting 0 from 18. So the delta T is negative 18 degrees Celsius. And if you recall, we use the specific heat of ice here because once we have frozen everything, we are in the solid state and we're working with ice. So the specific heat of ice was 2.03. And again, our grams canceled out, degrees Celsius canceled out. So Q3 will give us the same value as here, but it'll be negative. Okay. And then finally at the end, we're going to add all of these values up. So we have negative 32,008 plus negative 28,390 plus negative 3106. And when you plug all of those in, you're going to get the same number we had here, but it will be a negative value. So that will be negative 34, 602. And when you convert that to kilojoules, it will be negative 34.6 kilojoules. And here we don't have to indicate that energy is being released because the negative sign implies that it is being released. So those are the two different versions that you could use. They will both get you to the same answer, but the sign will just be flipped around depending on which version you use.